Welcome to this one more lecture on the scattering theory. And in this particular lecture, we will look at the concept of scattering by the potential field and the scattering amplitude, two of the important quantities in the scattering theory. So अब तक हम लोग जो कर रहे थे वो बहुत बेसिक था, वो सिर्फ टर्मिनोलॉजीज को डिफाइन करने का सिर्फ कुछ स्टार्टिंग थी कि जो टर्म्स हम लोग स्कैटरिंग थ्योरी में यूज करने वाले हैं वो असल में उनका मीनिंग क्या होता है, उस तरीके का कुछ। लेकिन जो रियल क्वेश्चन है वो ये है कि हाउ डू वी स्टार्ट स्टडिंग स्कैटरिंग थ्योरी इन क्वांटम मैकेनिक्स। द रियल क्वेश्चन इज व्हाट टू डू इन दिस स्कैटरिंग थ्योरी। वो कौन कौन सी क्वांटिटीज हैं जो कि कैलकुलेट करनी है और कैसे कैलकुलेट करनी है, दैट इज द इम्पोर्टेंट थिंग। सो जो क्वांटिटी कैलकुलेट करनी है वो तो स्कैटरिंग एम्पलीट्यूड, और स्कैटरिंग एम्पलीट्यूड की हेल्प से डिफरेंशियल and total cross section, which is the number of particles scattered in some particular direction. So those were the quantity that we are interested in. But हम लोग start कैसे करेंगे? The basic question is that, and the answer is very simple, because if you have to do anything with the within the quantum mechanics, you have to solve the Schrödinger equation. So कैसे start करेंगे? So we will start solving Schrödinger equation. ओके, तो श्रोडिंगर इक्वेशन स्टार्ट सॉल्व करने से पहले जो इम्पोर्टेंट थिंग है वो ये कि जो स्कैटरिंग थ्योरी हम लोग डेवलप करने की कोशिश कर रहे हैं वो किन बेसिक सर्कमस्टांसेस के लिए फॉर्मुलेट होने वाली है। सो बेसिक थिंग इज दैट व्हाट आर द बेसिक assumptions that we are assuming in the starting of the whole formalism. So the first thing is that we are developing the formalism for scattering theory, in which the scattering is elastic. So the first assumption is that we are only concerned with the elastic scatterings. And to give you the meaning of elastic scattering, let me give you some example of scattering processes. So scattering processes ऐसे भी हो सकती हैं कि कुछ एक इंसिडेंट पार्टिकल है जो कि टारगेट पार्टिकल से हिट करेगा और फिर लास्ट में यहाँ से वापस से कुछ सिर्फ दो पार्टिकल की स्कैटरिंग की बात करेंगे. सो लेट अस सपोज दिस इज पार्टिकल ए, दिस इज पार्टिकल बी. सो द वन पॉसिबिलिटी इज दैट this particle will hit to this particular particle and they will just move in some different directions. So in symbol we can represent this process like this. So particle A strike or collide with particle B, and the final result is just the same particle but in different directions. So that is one of the possibility. इस पर्टिकुलर सिचुएशन में दो पॉसिबिलिटी हो सकती हैं. एक तो ये कि जो दो पार्टिकल स्ट्राइक कर रहे थे, जो कोलाइड कर रहे थे, वो एग्जैक्टली सेम फाइनल स्टेट में भी एग्जैक्टली सेम हो. इसका मतलब यह है कि इनका या तो ना तो नेचर चेंज होना चाहिए, ये जो पार्टिकल्स हैं वो जो है वही रहने चाहिए. वो पार्टिकल्स ऐसा नहीं है कि इधर से इलेक्ट्रॉन्स चले गए, उधर फोटोन्स या कुछ और पार्टिकल्स बन गए हैं, इस तरीके की स्कैटरिंग भी होगी. तो वो वाली स्कैटरिंग हम लोग अभी कंसिडर नहीं कर रहे हैं. सो the elastic scattering means the nature of these particles must be same. Not only that, the internal state of these particles must also be same. Or internal state से क्या मतलब है कि let us suppose there is this atom, for example the hydrogen atom, and you are striking some electrons to that hydrogen atom. So the collision process will be elastic when the internal state of electron, which is just the electron itself, is and the internal state of hydrogen is same in the final result of the scattering. इसका क्या मतलब हुआ कि अगर ये हाइड्रोजन एटम है तो इसकी अलग अलग स्टेट्स भी होंगी, ग्राउंड स्टेट, फर्स्ट एक्साइटेड स्टेट, सेकंड एक्साइटेड स्टेट. सो फॉर एग्जांपल ये इलास्टिक स्कैटरिंग से पहले अपनी ग्राउंड स्टेट में था, तो इलास्टिक के बाद इस स्कैटरिंग के बाद भी ये ग्राउंड स्टेट में ही मिलना चाहिए, इसकी इंटरनल स्टेट भी चेंज नहीं होनी चाहिए. सो वो वाली सिचुएशन को बोलेंगे हम लोग इलास्टिक स्कैटरिंग्स, where the nature of the particles, which is electron and hydrogen, is not changing. The electron is electron, the hydrogen is a hydrogen. And not only that, the internal state of these two particles must also be same, right? If the hydrogen atom before the collision is in the ground state, then it must be in the ground state after the collision. So if those two conditions are satisfied, then that kind of process is called the elastic processes. So these are the processes that we are interested in, but there are more possibility. One is that initially we have particle A and B. Particle A and B are striking to each other. That means they have some kind of scattering, and it may happen that particle A is just same after the collision, but particle B, the nature of the particle B is same, but it has been changed its internal state right? So it may be that before collision it is in the ground state, and after collision it has been excited in the first or second excited state. So those kind of scattering are called inelastic scattering. Right, so this is elastic, this is inelastic. The third possibility is that you have particle A and B, they are striking to each other, and after the scattering, the result is some different kind of particles. When you will study the nuclear physics, the particle physics, you will see this kind of process is happening. You will have some different particles, and on the end result of scattering, you will have some different particles of different nature. Right, for example, you will have an electron and positron, and in the result you will have some two gamma photons. So that kind of processes you will study in the fundamental particle physics and nuclear physics. So these are called reactions. So if the nature as well as the internal state is same before collision, after collision, those kind of processes are called elastic scattering. If the nature is same but the internal state of one or two particle or both particles has been changed, those kind of scattering are called inelastic scattering. And if the whole particle itself, the nature of the particle itself has been changed, then those processes are called the reactions in the physics. Right, so that is just to give you introduction. Now we are restricted ourselves just to the elastic scattering, so the process where this kind of things are happening. Now the second assumption is that we are dealing with the non-relativistic situations. Non-relativistic now particles, you can say, because the particles we are dealing with, they are just moving with ordinary speed, at the speed which are very very small in comparison to the speed of light. So that is the second assumption, because if you will involve the relativistic effect, then there will be the reaction kind of thing. The particle may convert into some other particle. So those kind of processes are very difficult, and those processes can only be handled with the quantum field theory, right? Even the quantum mechanics that we are doing is an inadequate to deal with these kind of processes. So the second assumption is that we are restricted ourselves to the processes which are non-relativistic. The third one is that we are dealing with the spinless particle, the spinless particles, right? So we will assume that the particle that we are dealing with are spinless. Even we will study the electrons and protons, neutrons, that kind of particles as well, because and we know that those are fermions, so they have spins. But the formalism that we will develop is for spinless particles, and it will approximately give a good result. So the first thing is that what is happening in the scattering experiments. In this scattering experiment, there is some particle which are the incident particle, and there is some target particle. And we know that these incident particle will hit to these target particles. Right? Let us suppose this target particle is some kind of charged particle. Right? And these incident particles are also charged particles. It is just to give you example. It is not compulsory that these particles has to be charged particle, right? So if they are charged particle, we all know that these particles have some kind of field around them, right? And they will interact via these fields, right? And we know that we can describe this particular field by using the potential function. So let us suppose that the position of this particular particle is r1 the incident particle, and the position of this particular particle is r2 with respect to some origin. Then this particular vector and the magnitude of this particular vector will be r1 minus r2, right? And the situation that we are dealing with is that, or we are assuming, this is one of one more assumption. The assumption is that we are only dealing with the situations where the potential function, the potential energy in between these two particles, right, which is the potential energy, which in general will be function of r1 and r2. We are assuming that it is just the function of position of the distance between these two particles. So this is the assumption, right? It is not at all compulsory that, or it is not mandatory that it will be the situation in all the cases, right? Generally it is not true, but we are only dealing with those situations where the potential in between these two particles, which means the interaction between these two particles, the force, is just the function of the distance between these two particles. So this is the fourth assumption. So let me write it. The potential in between R1 and R2 is just the function of the distance between these two particles. So these are the four basic assumptions that we have to develop the basic theory, at least to start developing some mathematics for the scattering experiments, right? So this is just the basic. Now let me tell you how we will start developing the Schrödinger equation for this particular process. So what we are assuming is that the potential in between them is this one, right? And there is this some kind of frame. And let me just assume in this particular diagram that there is some center of mass of this particular system. So it is center of mass, and uh, let us suppose this capital R represent the position of this center of mass with respect to the origin O. Now we have to write the Schrödinger equation for this particular system, which is having two particles, right? So let me write the Schrödinger equation for this particular system. One more thing is that we are assuming the potential in between them is time independent potential, right? So if the potential is time independent, then the state of this particular system will be stationary states, and we have studied about the stationary states in the first second lecture of the approximation method. So if you don't, if you are not familiar with those kind of state, then you can go and check that particular lecture. But let me write this Schrödinger equation, time independent Schrödinger equation for this particular system, which will be minus h cross over 2 m1, right, for this particular particle into del uh, 1 square, which is Laplacian with respect to the particle 1, or for particle 1, or minus h square over 2 m2 Laplacian for particle 2 plus v of r1 and r2 into psi of R1 and R2 equal to ET, the total energy of the system, into psi of R1 and R2. So this is the Schrödinger equation for this particular system that we have to solve to get something about the scattering process, right? So, but the assumption that we are having, the first assumption is that the potential is just the function of R. So potential R1 and R2 is just the function of R, which is the distance between these two particles. So in this particular situation, what you can do, you can decouple this particular equation. You can write two equivalent equations out of this particular single equation. One is for the center of mass, right, having mass m1 plus m2, and other one is for some fictitious particle of reduced mass mu, right? So by assuming this particular thing, let me just write this particular part. So we can write the above Schrödinger equation into two independent equations, one for the motion of center of mass, right, and another for the motion of fictitious particle. So you all know about the fictitious particle, which are the pseudo particles. They are not the exact particle or actual particle. They are just the mathematical constructs. So fictitious particle of reduced mass mu, right? And this mu will be m1 m2 over m1 plus m2, right? Motion of this in the potential v of r in center of mass frame, in center of mass frame. So this is the result of just this particular basic assumption. That important this assumption is, right? We can convert this particular equation in two equations. One is just the equation for center of mass of this particular system, and another equation is for some fictitious particle of mass mu, which will be m1 m2 over m1 plus m2 in the potential v of r in center of mass frame. So what we did, we have converted this particular equation, which is in the lab frame. We have converted this problem into the problem in the center of mass frame. So by doing, or by assuming the potential to be the function of r only, we have converted the lab frame calculation into the center of mass frame calculation. Now we will see what the equation will be and how we will solve that equation in center of mass frame. So let me just rub it. So this is the way to start the scattering theory. We have to solve the Schrödinger equation, right? That is what we can do in this quantum mechanics. So what will be the equation for the fictitious particle? Or let me just tell you one more thing about this. This kind of thing you have did in your classical mechanics course, the central force motion, where you have studied the how to convert the two body problem into one body reduced mass problem. So it is let me just say this way that if v of r1 and r2 is just the function of r, then the problem is just like the problem is just like the particle in two body problem, like the two body problem in classical mechanics. And there you can convert that particular two body problem into one body problem. You all have studied that. I'll not go into the mathematics of that thing, right? So what will happen is that you can write the Schrödinger equation for fictitious particle, right, moving in the potential v of r. So now we can write the Schrödinger equation for fictitious particle of mass mu, right, moving or in the potential v of r, right? And it will be time independent Schrödinger equation because the potential is time independent. So it will be like h cross over 2 mu, right, mu into Laplacian plus v of r into psi of r is e into psi of r. And this is the Schrödinger equation which we have to solve in order to get some result for scattering theory. Now this is the Schrödinger equation in center of mass frame, right? And this particular wave function will give us the information about the particle of mass mu scattering in the potential field v of r, right? So what we have did is that, or what uh, we have done is that we have converted the problem two body problem in the lab frame. We have converted that problem to the one body problem in the center of mass frame. And now in the center of mass frame there is this particle, right? In the center of mass frame, how you can just look at the problem is that from the center of mass frame there is this potential, right? So there is this potential v of r, and there is this particle of mass mu, right? It is coming towards this particular potential. It will interact to this particular potential, and this potential field or potential will scatter the particle. So this will be the situation. Now the distance, right? So this r which we are using is the distance of the particle from the center of potential v of r. So this particular distance is r. So we have converted this particular process from lab frame to the center of mass frame, where now the problem is the scattering of particles with mass mu scattering from the potential field v of r, right? So this is what we have done in this particular lecture. We have converted the problem. It is just this thing that what we did, right? So let me write it like this. So the conclusion of the whole lecture is that we have converted the problem of scattering from lab frame to the problem of scattering of particle with mass with mass mu by the potential field in lab frame, sorry, in center of mass frame. So now what we will do in the coming lecture, we will solve the problem in the center of mass frame. That is what I said in the first lecture, that the calculation that we will do those calculations in the center of mass frame only. And then we will use the results that we have derived in the previous lectures to uh, calculate the results in the lab frame. Right. So the starting of the problem or solving this scattering theory is that we have to first convert this Schrödinger equation from the lab frame to the center of mass frame, right? And now we have to solve this particular equation, which is representing the scattering of single particle having mass mu, the reduced mass, the scattering of this particular particle from the potential field, right, which is just the function of r. Initially, it was the scattering of particle 1 from the particle 2, and it was difficult to solve in that frame. So we have just converted the problem in the center of mass frame, and it is like the scattering by a potential field. And this is what is the meaning of scattering by the potential field. We have converted the whole problem to the center of mass frame. And now in the coming lecture, we will calculate the expressions for the scattering amplitude, right, and the other quantities. So this is how do we start doing the scattering theory, right? So this is it in this particular lecture, and